Hey guys, in this video we are going to talk about 2.1 and 2.2 in the textbook. We're going to talk about input and output and how we can use the definition of a function as equations, graphs, and tables to figure out inputs and outputs. And then in 2.2 we're going to look at the domain and range of functions algebraically and graphically. So let's go ahead and get started. So the first question I have is, what is a function? Okay, um, so you may have remembered this definition from the last time you took an algebra class, but I think the easiest way to think about a function is something that has an input and gives you an output based on some kind of rule, okay? So for example, um, they started 3D printing houses, okay? And so how it works is you have some material, some kind of concrete material that's used to print the house. And you take this material and you feed it into a 3D printing machine, and you give the machine a blueprint for what to do with this cement, okay? And the machine reads the blueprint and makes something like this, a house, okay? So in this example, our input is the concrete, right? We're taking this thing and we're shaping it based on some rule. Okay, so a function has three things. The first one's an input. The second one is the rule that directs the input, right? Tells the input what to do. So the rule in this case is the blueprint that's given to the 3D printer. Okay, and the last component of a function is the output. So the output is what happens to the input given the rule. And what happens is it makes a house, right? It makes a 3D printed house. So we take the concrete, that's our input, we apply the rule or the blueprint, and then our output is going to be something like this, 3D printed house. So that's just kind of an intuitive way to think about functions, I think. And there's a bunch of different ways that you can think about it, but anyway. Okay, so recall that a function is just a rule that turns an input into an output. And we just talked about this. So in our 3D house example, our input was our concrete mixture. Our rule was the blueprint that was fed to the 3D printer that tells the printer how to make the house. And the output is the actual house, the finished product, okay? So we are going to look at functions in terms of inputs, outputs, numbers, and rules, okay? So instead of having something concrete like the 3D printed house, we're going to talk about just rules that we do with numbers, okay? So for example, let's say I have this rule that says add 3 to the input, okay? And let's say that we feed this function an input of 4. What's my output? Well, the rule tells me to take my input and to add 3 to it, right? So once I do that, my output is now 7. So this is my output. This is my input. And this was my rule. My rule told me to add 3 to the input. Now, in algebra, we usually represent the input with an x and the output with a y, or an f of x. So examples of functions, we could have something like, we could have f of x equals 3 times x, okay? So this is our input. We can put in anything we want for x. It doesn't have to be 3 or 4 or 2. We can put in anything we want. And we're always going to get an output, right? And that's our f of x. So we could make a table for this if we wanted to. We have our input on the left usually and our output on the right. And we use our rule to fill in the table. Okay, so for our inputs, we can just make them up. We don't use the rule to find our inputs. We can just, make up some numbers, -2, -1, 0, 1. Those numbers will work. And so to find our outputs, we apply the rule. So the rule is multiply every input by 3. So we take our -2 and multiply it by 3. That's our rule. And that gives us an output of -6. So the input is -2 and the corresponding output is -6. Okay, we can do the same thing with the next one. -1 is our input. We apply the rule, which says take the input and multiply it by 3, and we get -3 as our output. We can do it with 0 as well. Take 0, multiply it by 3, that's our rule, and we get an output of 0. And our last one is 1, so our input is 1. We're going to take 1 and multiply it by 3 like our rule says, and we get an output of 3. So the corresponding output of 3 is the input of 1. Okay, see how that works? All right, so let's see what's next. Now we're going to look at functions as in 3 different ways. We're going to look at them as equations, we're going to look at them as graphs, and we're going to look at them as tables. So the first thing is equations, or rules written with variables, okay? So it says evaluate f of -3 for this function. It says f of x equals 3x squared plus 6x plus 7. Now, what this is telling me is -3 is my input. I'm going to input -3 in anywhere I see a variable. In this case, our variable is x. So let's go ahead and do that. All right, so what is our output? Well, we have f of -3 is equal to 3 times -3 squared plus 6 times -3 plus 7. So anywhere I see an x, I plug in a -3. So on the right side, if I do PEMDAS, -3 squared is 9. So what I end up getting is 3 times 9. 6 and -3 multiplied is -18 plus 7. And so I end up getting 27 minus 18 plus 7. And let's see what that is. It's going to be 9 and 7 is going to be 16. So this is our answer here. When we evaluate, we're given an input and we find out what our output is by using our rule. All right, let's do the next one. Evaluate g of 2 for the function g of t equals, actually, maybe we should have made this x. Let's change this. G of x equals 7x over 4 plus x. So this is our rule that I'm boxing in red, and our input is 2. So wherever we see a variable x, we're going to input 2. Okay. And then we're going to figure out what output corresponds to an input of 2. All right, so g of 2 is going to be 7 times 2 over 4 plus 2. Okay, and that's going to give us 14 over 6, which reduces by 2. If we divide top and bottom by 2, we get 7 over 3. So 7 over 3 is my output for my input of 2. Okay? All right, let's look at the next one. If r of t equals at squared minus 6, find r of negative 2. So negative 2 is my input because it's in the parentheses. And my variable this time is t. So my negative 2 is going to go anywhere I see a t, which is only in one spot, okay? So we have r of negative 2 equals a, which we're just going to leave it alone because we only plug in the number for the variable that is in the parentheses. Okay, so negative 2 squared minus 6. So if we simplify this out, negative 2 squared is just 4. We end up getting 4a minus 6. And it's okay that it's not a number. We have a variable still in there, but it's still valid. It's still going to be our output. So when our input is negative 2, for our rule at squared minus 6, our output is 4a minus 6. Okay. All right, let's look at the next one. This one is a little bit more involved, but it's still the same principle. Okay. So now we have this rule 5x squared minus 1 equals g of x, and we want to simplify this guy, right, by using our rule, our function notation. So we have our input right here. So this is our input. And we have another spot where we're going to have to do our input. Okay, and then the bottom we don't have a g, so we'll just leave that as it is. So let's figure out our first output for our input of x plus h. So we have g of x plus h equals. Now remember, all we're doing is we're replacing x plus h anywhere we see a variable x, right? So g of x plus h is going to equal 5, and then I'm going to replace x in my original rule with x plus h squared minus 1. Okay? Now I can simplify this out by foiling, right? Because I have x plus h squared, so I need to expand that out into x plus h times itself. That's what squared means. And I'm going to FOIL this using first, outer, inner, last. I'm just going to kind of leave the 5 out in the front. Okay? And then the minus 1 at the bottom. So let's go ahead and FOIL this. So first is x times x, gives us x squared. Outer is x times positive h, is a positive xh. Inner, again, h times x is again another positive xh. And last, h times h is a positive h squared, right? All right. We can simplify this more by combining like terms. These guys are like, so one of them plus another is 2 of those things. And we get 5 times x squared plus 2xh plus h squared minus 1. Now we can multiply that 5 that's on the outside into everybody. So this is 5x squared plus 10xh plus 5h squared, and we still have this minus 1 hanging out in the back. And that's all we can do. We don't have any like terms, so we have simplified g of x plus h into this guy. And we're just going to leave this for now until we put it back into the function. Okay, so g of x, we're simply putting x into our rule, which is already done for us, right? So g of x, we don't have to really do anything crazy. Our input is x, and we're putting x into our rule, which is already done. So it's just 5x squared minus 1, and nothing else can be done here. Okay, so this is our g of x. So we simplified the top, and now we can simplify it all together. So I'm just going to replace g of x plus h with what I found, 5x squared plus 10xh plus 5h squared minus 1, and then minus g of x, which I'm going to replace with 5x squared minus 1. That's what I found. So now the top we've replaced, and the bottom is just h. We didn't do anything there. Now, this minus distributes to both of these guys, and what's going to happen with that is these 5x squareds are going to end up canceling, and this negative times negative 1 becomes a positive 1, so these 1's are going to cancel as well. And what we get is 10xh plus 5h squared, all divided by h. The last thing that we can do is on top, we can factor out an h. So if I pull out an h, which means I just divide both of these guys by h, what I have left on the inside is 10x plus 5h over h. And the last thing we can do is divide out these h's. So my final answer, simplified, is 10x plus 5h. This is my final answer here. Alright, so we can also look at functions as graphs, okay? So it says in the figure below, estimate f of 3. So remember, our input goes on the horizontal axis. That's our x values. And the output goes on the vertical axis. Those are our y values. Okay? So f of 3. So what we're looking for is an input of 3 on our horizontal, and we look at the corresponding y value. So how high is this graph when x is 3? Well, the answer, it looks like it's just at 0. Let's see. 1, 2, negative 1, 1, 2, 3. Yeah, so it looks like it's just at 0, right here. So when we can write it as an ordered pair if we want. When x is 3, f of x is 0, like that. And so that tells us that when our input is 3, our output is 0. Okay. Okay, the next one says, for which x value is f of x equal to 4? This time we want to find the input, right? We want to find the input when the output is 4. So where is the height 4? Okay, think about that. Where is the height on this graph 4? Well, it looks like the height is 4 about right here, right? Okay, and so it looks like the x value is at 1, right? So this is 1, 2, 3, 4, and so forth. So our x value is going to be 1. When x is 1, y is 4. And the last question says, for which x values is f of x greater than 0? Or another way of saying this is, for what x values is f of x positive? Alright, so where is f of x positive? That's going to be when the height is positive, right? And the only place the height is negative is right here. The height's negative there, and right here. So the height is positive anywhere else except those little red pieces. So the x values where f of x is positive is going to be, let's see, we could say that x is between, but not including, because we're doing strictly greater than 0. We could say that x is between negative 1 and 3. So if x is bigger than negative 1 and less than 3, then f of x will be positive. So that's our answer here. Okay, use the graph of f of x to estimate the following. So we're not gonna have exact answers for all of these. We might have to estimate. So the first one is, what is f of 0 given this graph? Okay, so let's just highlight our x-axis, which is going to be this horizontal axis right here. So that's our x-axis. And then our y-axis is going to be right here. That's our x and our y-axis. So our input, when our input is 0, what is our output? That's what question A is asking. So when the horizontal value is 0, what is the vertical value? Well, when our horizontal value is 0, that's right here, right? So our vertical value is going to be this guy, right? So when our horizontal is 0, our vertical is about, it looks like it's about at 24. So let's just say that. Our output is 24. And we could write this as an ordered pair if we wanted to, just to see something that you're used to seeing. Our input 0 and their output that goes with it is 24. So when x is 0, f of x is 24. Okay? All right, what is f of 1? So this time, again, we're given our input is 1, and that's on the horizontal. So we look for this. Our input is 1. What is our corresponding output on the curve? Well, that is going to be right here, right? And that looks like it's right at 10. So our output is 10. If we wanted to write this as an ordered pair, we would say x is 1, f of x is 10. Just like that. Okay. Let me go ahead and erase some of this just so it's not so messy. Let's see. Okay. All right, so the next one is f of b. So b is not a number, but that's okay. We're looking at, it's in the parentheses, so it's an input. So that means we're looking at the horizontal axis. So that's right here. So when x is b, whatever that may be, what is f of x? Well, we look to see where b intersects that curve, and that happens right here. And that looks like, let's see. It looks like if we're looking at the y-axis right here, I would say that is at negative 8-ish. Let's just say negative 8. Okay. So again, our input comes first in the ordered pair. That's b, whatever that is. And then our output is negative 8, which is f of x. Okay. All right, next one is f of c. So again, we look for it on our horizontal axis. That's right here. And where does it hit the curve? Well, it hits it at a vertical value of 0, right? So this is going to be 0 height. All right, so that's going to be 0. And our ordered pair is c, comma, 0. Okay, let's see. F of d. So again, we're just going to look at our horizontal axis. We see d is over here. Where does d intersect the curve? If we draw a vertical line, that happens at a height of 20. All right, so when my input is d, and my horizontal is d, my output is 20. Okay. All right. So the next one says, what is f of 0 minus f of 1? Well, that's easy because we have numbers now, right? We found in part A that f of 0 is 24, so we can just replace it because that's how equality works. So that's 24. F of 1 we found in part B is 10, so that's just 10. So 24 minus 10 is just 14, and that's our answer. Okay. Oh, I forgot for part E. We should probably write 20 right there. All right. And part G says, what is 2 times f of b? Well, 2 times f of b we found in part C to be 8, right? Or no, -8. So we just replace f of b with -8. So 2 times -8 is going to give us -16, and that's our answer here. All right, we can also talk about functions in table form. So sometimes when you're given a rule, you can make a table if you'd like. It might be helpful to do that. But anyway, let's look at the table and see if we can figure out these answers. So part A says, what is g of 3? So what are we given? We're given an input. So we need to look in the input column. That is my x column. Okay, and then my g of x on my right is going to be my output. Okay, so we're given an input. So when the input is 3, right there, what is its corresponding output? That's what part A is asking. And we can see right to the right, it's 7. So my answer is 7. Okay, the next one says, for what input is the output -5? So this time we're given an output because it's not in the parentheses. So it's asking what input has an output of -5. So we go to our output column and we find -5, which is right there. And then we look over and we see to the left that the input that goes with -5 is going to be 0. Okay, so my answer here is 0 for part B. That's what goes in that parentheses. Okay, next one, g of 0 equals what? Well, we're given an input because it's in parentheses and we're looking for the corresponding output. So this is kind of, goes hand in hand with part B because basically already did it. Let's see. So yeah, here's my input of 0. My corresponding output is -5. So that's my answer here. And finally, part D, what is the input that has an output of 0? So we look at our output column and we find 0, which is right there. And we look to the left and it says our corresponding input should be 11. So that's my answer for part D. Oops, my bad. Okay, we can also make tables. All right, so it says make a table for a function h of x equals 2x plus 3. So let's just make a table. Typically our input's on the left, which is x, and our output's on the right, which is h of x, or 2x plus 3 in this case. H of x, same thing. So for the inputs, we can just make up numbers because we weren't given specifics. So maybe -10, -2, I don't know, I'm just making up stuff. 4, 6, okay? So we have to make up the inputs, but then the rule is going to tell us what the corresponding outputs are. So for example, for 10, or -10 rather, we have our rule tells us to put in -10 for x, and our output is going to be -20 plus 3 is -17. Okay? Next one is -2. So we have 2 times -2 plus 3. So that means my output is going to be -4 and 3 makes -1, and so forth. So we have 2 times 0 plus 3 times 3. Okay. All right, so these are our outputs that we found from our corresponding inputs. And our 2x plus 3 was our rule, okay? So that is pretty much all the components of a function, okay? So yeah, that is going to be it for this video. I'm going to make a part 2 for this next section, domain and range, but I hope you guys enjoy, and I'll see you for the next video. Hey guys, in this lecture we're going to talk about section 2.2 in the textbook, domain and range. So let's just get into it. The domain is all possible inputs that a function can take. In other words, all possible x values that are valid for a function. And the range is all possible output values given the domain. Or another way of thinking about it is all possible y values that a function can have. And so I want to kind of illustrate this with a silly example of these ice cube trays. And as we know, the function associated with ice cube trays is to freeze liquid and make cubes, right? And they don't necessarily have to be, ice, like cubes of water. We can put really any kind of liquid we want into these trays and freeze them and make cubes, okay? So what is the domain in this case? So what is the domain of the function of freezing liquids into ice cubes? Well, the input, what can we put in these ice trays? Well, really we can put in any liquid, right? That is going to be the valid input. We can't put in, a random object like a sock or a pen or a taco or something and expect them to freeze and become cubes, right? And so the valid input here is any kind of liquid that freezes. Now, what's the output? So what are the valid outputs? Well, it's just going to be frozen cube shape liquid. Right? That's the only possible thing we can get out of these ice cube trays when we put liquid in there and we freeze them. Okay? So it's kind of a silly example, but that is sort of the intuitive idea of domain and range. Okay, so let's start with a simple example. We're going to start by finding the domain and the range from a table. And when we do this, we're going to have a finite number of values, meaning that we can count them, right? We don't, we can count all the inputs and we can count all the outputs in this table. And so that means that our domain and range are going to be finite as opposed to infinite. So let's start with the domain. So for the domain, we are looking at our input column, which is the x column, and we're just listing all of the inputs that we have in this table. So we have -5, -2, 0, 3, 4, 7, and 11. And for our range, we're going to do the same thing except with the output column. So we're just going to list our output values: 9, 3, -5, 7, -4, 10, and 0. Okay, so that's our domain and our range from a table. So the next thing we're going to do is we're going to find the domain and range of functions, meaning something like this. So y equals 3x minus 1, f of x equals 2x squared minus 9, things like these, right? These are all functions. And functions have infinite domain and ranges because typically functions can take on infinite values. And so there's two ways to look at these. The first one is graphically. I think this is the easiest way. And the second way is algebraically. So let's do some examples where we find the domain and range of a function graphically. Okay, so what you want to ask yourself when you're doing these for the domain, since we care about inputs, remember on a graph, the domain or the input axis is horizontal, okay? And so what we want to ask ourselves when we look at these graphs is how far left does it go to how far right does it go? Okay. And in a similar way, for the range, we're going to ask ourselves, how far down does this thing go to how far up does it go? Because output is vertical. So let's do some examples. The first one is we want to find the domain and the range of this function, 3x plus 2. And what you should do is you should go to desmos.com for these problems and for your homework problems. And once you go to desmos.com, you can just type in this left-hand tab, we're going to type in our function, which is 3x plus 2, and Desmos is going to graph it for us. Okay, and we can see that it's a line, and so the first question is how far to the left to how far to the right does it go? And we can see if we keep panning down, it's moving very slowly to the left, but still moving to the left nevertheless, forever, indefinitely. And if we pan back up, it seems to move to the right forever as well. And so the domain is going to be everything, all real numbers. All right, so let's write that here. So the domain is all real numbers. Anything we want to put in, we can put in. Another way of looking at it is what can we put in here for x? We can put in whatever we want, all real numbers. All right, so let's look at the range of this line. So how far down to how far up does this thing go? Well, again, if we pan down, it goes down indefinitely, forever and ever and ever. And if we pan up, it also goes up forever and ever. And so the range is also going to be all real numbers. All right, well, let's look at the next one. What's the domain and the range of this function? Negative 2x squared plus 1. Well, again, I'm just going to put it in Desmos. So negative 2x squared plus 1. And let's see if I can, I might have to close out because the window's kind of weird. Maybe I can just, so I'm clicking this wrench, and I'm going to adjust the x and the y values. I'm going to go from 0 to 100 for x, and I'm going to go from negative 10 to 10 for y, just to get a better picture here. And then I'm going to just sort of pan. Okay, so there it is. There's the graph. So first question is, what is the domain? What sort of values can I plug in for x into this function? Or another way of thinking about it is how far left to how far right does this thing go? Well, if you keep zooming out, you're going to see that it goes to the left. It seems to be going slowly, but it does go forever and ever and ever in the left direction. And in a similar way, it goes forever in the right direction. Another way of thinking about this is that there are no restrictions to what we can plug in for x. We can plug in 1,000,000 for x and get an output. We can plug in 1 over 10. We can plug in anything we want for x. There's no rules. So for that reason, the domain here, again, is going to be all real numbers. But the range is going to be different because, remember, the range is how far down does this thing go to how far up does it go? Well, it goes down indefinitely, right? We can just keep scrolling and it goes down forever and ever and ever. However, it does not go up forever. It stops, and if we click this little point at the very top of the mountain here, it stops at y equals 1. That's our highest output value. So how can we say this? We can say that anything less than or equal to 1 is in the range. So since range is output, that's our y. So y is going to be anything less than or equal to 1. All right. Okay, so let's do this next one. H of t equals 3 over t minus 5. Now, Desmos recognizes x as our independent variable, so I'm just going to put in x where I see t. So I'm going to put in 3 over x minus 5. Okay, and let's zoom out a little bit. All right, so let's start with our domain. Okay, so the domain is all valid, all possible values of x that we can put in. Well, how far to the left does this purple go? Well, it looks like it goes on indefinitely to the left, right? So it goes on forever to the left, and then we pan back, and it kind of stops. It seems to stop, and there's like a jump from the left purple graph to the right purple graph. And that jump appears to happen where this graph sort of hugs an x value. And that x value is going to be x equals 5. And let's think about why. So let's put in x equals 5, and just to see, you see how it's hugging that line on both sides? That's going to be an excluded value in the domain because it's never going to touch it. It's going to get really, really close, as we can see, but it's never going to touch it. And the reason algebraically is because if we plug in 5 into 3 over x minus 5, well, what we end up getting is 3 over 0, and we can never have 0 in the denominator, okay? So what is our domain? Our domain is going to be everything except x cannot equal 5. All right, so our domain is going to be all reals except we can't have x equaling 5. All right, so let's check out our range. So our range is how far down does this thing go to how far up does it go? Well, if we scroll down, our purple graph seems to go down. Let me get rid of this x equals 5. Our purple graph seems to go down forever. And if we pan back up, it jumps, right? It goes from this lower purple graph to the higher purple graph, but there's a jump, okay? And the jump, again, is where these curves start to approach, okay? And if you notice on the left side, it gets really, really close to 0, but it never touches it. And the same thing happens on the right side. It gets really, really close to 0, right? But it never actually touches it, okay? So, and we can put this in here to just, kind of get a visual. Y equals 0. So that is our range restriction. The graph is never going to touch that output value. And another way of seeing this algebraically is 3 divided by something. Is that ever going to give you 0? No, you are never going to get 0 from that. And so my range is going to be everything except 0. So the range is going to be all reals except my output, h of t, in this case, can't be 0. And I should probably change x to t up here because that's our variable. Okay? Alright, so that's that one. Let's do another one. I'm just going to do a bunch of examples because I know this topic can be kind of difficult when you first see it, but you get used to it after a while. So the next one is the square root of x squared minus 9. Let's put it in. Okay, so what is the domain? So domain is x values. Well, if we're coming from the left, okay, it seems to go to the left indefinitely. So it comes from the left indefinitely, and it kind of stops right here at this x value, x equals -3. And it jumps, so it jumps from x equals -3 to x equals 3 without covering any of the x values between -3 and 3. And so our domain is going to be that x is either less than or equal to -3 or greater than or equal to 3 because, it covers those areas. So our domain in this case is x is less than or equal to -3, or x is greater than or equal to 3. All right, and what's our range? Our range is how far up to how far down does this thing go? Well, if we look, the smallest output value is 0, but it goes up indefinitely, right? So all these other y values are accounted for. And so my range is going to be anything bigger than or equal to 0. So g of x is going to be bigger than or equal to 0. All right. Okay, let's do one more on this slide. So we have f of x equals 1 over 40 square root of 49 minus x squared. Let's see. All right, so we get this weird U-shaped thing, right? All right, so what's the domain? So this is a little bit tricky, because what happens is if you go on Desmos and you try to like move to the left, it kind of stops when it gets close to -7. Like it just kind of disappears like that if you try to pan to the left. So it gets super close to -7, but it actually doesn't touch -7. And on the right, we kind of have the same story. It gets super close to 7, but it never actually touches 7. It kind of just goes away. And we can see that in our function algebraically, because what happens if we plug in 7 for x? We get 1 over square root of 49 minus 49, which ends up being 1 over 0. We can't have that in both cases when we plug in -7 and +7. And so the domain is going to be between -7 and 7, but not including those, right? So what is our domain? Our domain is anything between -7 and 7. And we're not including these, and we can see that we're not including because the less than and the greater than don't have a line underneath these. So we exclude these values. All right, so what's our range going to be? How far down to how far up does it go? Well, we can see from this graph that the lowest point that we're going to have is when x equals 0. That's the lowest point. And that happens at 0.143. In your homework, it might ask you for a fraction or an exact value. So if I put 0.143 in here and I click on this blue thing to the left of it, it's going to give me a fraction, 143 over 1,000. Wait, is that right? 143, yeah. So, yeah, so that is going to be, I think it should be, yeah, so let's just put 0.143 in there. So f of x is going to be greater than or equal to 0.143. Okay. All right. Let's do some more examples. All right, so find the domain and range from this graph. So let's do domain first. So remember, domain is how far to the left does it go to how far to the right does it go. Well, the leftmost value starts at -2, and it continues on straight. There's no jumps or anything. So it goes on until x equals 2, right? So the way that we can write this is we can write it in something called interval notation. So we can say it starts at -2 and it goes up until +2, like that. And I'm using brackets instead of parentheses because these closed circles on the endpoints tell me that those points are included. So we use brackets there. Okay, so what's the range? Well, the range is how far down to how far up does it go, right? So how far down to how far up does this thing go? Well, how far down? Well, the lowest value is at y equals -2. So again, and that's included, so we're going to just put -2 there. And what's the highest this thing goes? Well, the highest is at this point right here. Right, this is the height. And this looks like it's at a height of 3. So 3, and we're including it because our dots are closed. So that's the domain and the range for this function right here. Let's do this example. So this one's a little bit a little trickier, but it's okay. So let's do the domain first. Domain is how far left to how far right does it go. And we have some jumps, so we want to be careful, okay? So how far to the left does this thing go? Well, this arrow right here is telling us that it goes on indefinitely to the left, all right? So it starts at -infinity, and we're putting parentheses anytime we see an infinity. So it goes on indefinitely to the left, and then it kind of creeps up, and it stops right here at x equals -1, right? So since there are open dots on both of these like parts of the curve, we're not including -1 in here. So we're going to use parentheses to denote that -1 is not included. Okay, then we're going to union it. Okay, we're going to travel on the curve. So the curve ends, this curve ends, but we can still travel from x equals -1 on this curve down here. So that goes from x equals -1 to x equals 4. And again, we're not including 4 because of that open dot. Okay, and we're going to union it again because look, we can jump up to this curve. We're going to union it with, well, it starts at x equals 4, and this arrow tells me that it goes to the right indefinitely. And of course, for infinity, we're always going to put parentheses. So this is our domain. It's kind of split up into 3 little parts, but yeah, that's how you do it. So let's do the range now. Let's do the range. The range is going to be how far down to how far up does it go. Okay, so again, I can start how far down. Again, this arrow is telling us that it goes down indefinitely. So it starts at -infinity and it starts traveling up and up and up and up and up, and it stops, right? And it stops at y equals -1, but not including -1. Then there's a jump, right? There's a bunch of y values that don't get hit, right? There's a jump until right here, right? So we jump all the way up here to y equals 2. So we're going to union this starting at y equals 2, and the arrow tells me it goes off up to infinity. So that is going to be my range here. All right, let's do this one. So we don't have any arrows, so we don't need to use infinity here. Let's look at the domain first. So the domain, how far left to how far right? Well, it starts here at x equals -5, and it's a closed dot, so we include it. So it travels to the left all the way to this guy right here. So this guy happens at x equals 1, and it's a closed dot, so we include it. And then there's a jump in x values, like from here to here. There's a jump in x values. We're not including anything between 1 and 2. And there's like a million number, not a million, there's infinite numbers between 1 and 2. But we don't include them here because there's a jump. So we're going to union this with starting at 2, but not including 2 because of that open circle. 2 to x equals 5, including 5 because it's closed. All right, so that's our domain. Now let's look at our range. How far down to how far up does this thing go? What's the lowest value it has? Well, this looks like the lowest y value, -2. And it's a closed dot, so we can put that in parentheses. And this one's kind of weird because, it goes up, 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 but then there's like a jump, but there's actually not really a jump in the range, because if we just look at this curve right here, like we follow this thing to right here, but then we hop over to this guy and it's defined right here, right? So we hop over here and then it still comes up, right? So this thing, actually, there's no hole. There's no gap in the range because we have these two separate curves that we can work with. There's no gap. So it goes from y equals -2, right? And then we can jump over here. We can do that. To y equals 4 is the highest value that this curve touches. And it's included here. So we can put the bracket. So yeah, you should really think about this problem, because there is a distinction between domain and range. So think about it. Why are we not allowed to do the same thing that we did to the range for the domain? You should really think about this problem, because yeah, it kind of illustrates the whole idea of domain and range with graphs. Okay, so now let's do some problems where we find the domain and the range algebraically. Okay, so there's only two problems that I alluded to earlier with the domain and the range, or rather the domain. The first problem is that we cannot have a negative under a square root. Okay, so if there's a variable under a radical, we need to watch out. And the second thing is that we can't have 0 in the denominator. Okay, so if we have a variable in the denominator, we need to watch out. And these are the only two things we need to watch out for. If we don't have a radical and we don't have a denominator, the domain is going to be all real numbers. Okay, so let's look at this. Find the domain and the range algebraically. Okay, so I'm not going to focus too much on the algebraic side of the range, because it's kind of tedious to do, but maybe we'll just do it for this example to just kind of show you how it goes. Okay, so what do we have? We have an issue. Let's look at our issues. We have a variable in the denominator, right here, x. And so what we do when we have a variable denominator is we take the denominator and we say that this denominator cannot equal 0, right? That's our restriction. And then we solve for the variable by, just subtracting 9 on both sides. And we get x cannot equal -9. Right? Because if x equals -9, the denominator ends up being 0. So what is our domain? Our domain, if we want to write it properly, we can say all real numbers except x can't equal -9. Okay. So for the range, I'm not going to go into how to find the range algebraically, because you can use a graph to do this. So let's just use a graph, all right? So we're going to plug in 3 over x plus 9 to find the range. All right, how far down and how far up? Well, again, since we have this rational function, there is going to be, these curves are going to be hugging something, right? Horizontally, which is our range restriction. And it looks like they're both hugging y equals 0. And if we plug this in here, y equals 0, we can see that that is, let me make it a different color. We can see that that's the case, right? This curve is never going to touch y equals 0, but it's going to get really close to it. Another way of seeing that is 3 over x plus 9. Is there any x value you can put in here to give you an output of 0? No, there's not. 3 divided by what is 0? There's no such thing. Okay, so our range is going to be all reals except f of x can't equal 0. Okay, so that's our range. Okay, let's do this one. Find the domain algebraically. It doesn't say anything about the range, so we'll kind of leave that alone for another day, maybe in calculus. Okay, so we have a problem. We have a variable in the denominator. So what do? We take the denominator and we say that this denominator must not equal 0, or else there's a problem, and we solve for x. So I subtract 7 on both sides to get 2x cannot equal negative 7, and then I divide both sides by 2 to get x cannot equal negative 7 over 2. So our domain, we just found it algebraically, is all real numbers, except x can't equal negative 7 over 2. All right. Okay, so we have a problem. We don't have a denominator, but we have a radical. Okay. In particular, we have an even indexed radical, and the index is this guy right here. It's understood to be 2. So what's the restriction? Well, the restriction is that whatever's under the radical can't be negative. And how do we say that mathematically? Whatever is under the radical, which happens to be 2x minus 3, better be either equal to 0 or bigger than 0. That's how we say it. And then we just solve for x, okay? So how do we do it? Well, we can add 3 to both sides and divide by 2. So we get x is greater than or equal to 3/2. So our domain is going to be all reals. Well, actually, no, we don't have to say that. We can just say our domain is everything bigger than or equal to 3/2. That's our domain. And what's our range? Well, I'm just going to use Desmos to do this. So we're going to plug in the function square root of 2x minus 3. So my range, it's going to start at an output of 0, and it's going to go up forever and ever and ever. All right. So my range is going to be h of x is 0 or bigger than 0, and we can say it like this. Another way we can say it in interval notation, if we wanted to, for the range, we can say that it starts at 0, including 0, and it goes all the way up to infinity. And for the domain, we can say that it starts at 3/2 and it goes all the way up to infinity. So those are two different ways of writing the domain and the range. Okay, let's do one more example and then this video will be over. Alright, so we have some restrictions here. We have a denominator, we have a variable in the denominator, and we have a radical. So this thing right here better not equal 0. And also 9 minus x squared better be bigger than or equal to 0, but it can't be equal to 0 because then the denominator would be 0, right? So we have to say 9 minus x squared better be strictly bigger than 0, right? We're not going to put equal because if it's equal to, then we have a problem with the denominator, right? Can't have 0 in the denominator. Okay, so then we go ahead and solve for x. And so what we're going to do is we're going to add x squared to both sides to make it positive. So we get 9 bigger than x squared. And since this point is facing the x, I can write it like this. I can write x squared and just kind of like, I like the x on the left. I don't know why. I can write it like this. And then I can take the square root of both sides. Now, when I take the square root, I do plus or minus. And when I tack on a minus, the sign flips. Okay, so what I have is I have x is less than positive 3, and x is greater than negative 3. That sign's going to flip when I tack on that negative. And so I can write this in the following way. I can write that x is sandwiched between 3 and, or actually, minus 3 and 3. Right, so this is my domain. This is where x lives, between negative 3 and 3. And my range, I can just use the graph, okay? So I'm going to put 1 over square root of 9 minus x squared into Desmos. Okay, and so we have this weird kind of U shape, right? We can see that the lowest value happens at 0, right? And yeah, so that output is 0.333. However, your Wiley Plus assignment might want you to write an exact answer, okay? So if we actually plug in 0 into the function for x, if we plug in 0 into this function for x, we end up getting 1 over the square root of 9, which is just 1 over 3, okay? So our range is going to be that, what is it, y? So y is going to be anything bigger than or equal to 1 over 3. Okay, because like if we look at it again, you know, the range is how far up does it go? It goes on up forever and ever. Alright guys, well I hope this video was helpful. I'll see you guys next time. Thanks for watching.